Hey, computer's closed, paper notes open.
Oh,
Oh, no. Get over yourself. Let's go, bring it around. See what kind of markers I've got that are actually where red's actually working. Orange is actually working.
bro, you have a
Alright.
pack.
Bruh.
Yeah.
Bruh. Okay. Waiting on you all. Thank you. Alright, so today we're continuing. We did a lesson on seafloor spreading yesterday. We got 2 more. We're going to plow through this. Guys, that means I'm not going to read everything word for word. So when you do the questions, you might need to go back in the reading because I'm not going to read every word for word. Okay, I'm going to blast over this to give you kind of a big picture, and then you guys need to dig down into it. Okay, magnetic evidence for seafloor spreading. Guys, that looks like a terrible wallpaper from I don't know what.
It looks like a TV when it like.
Yeah, the test code,
Yeah.
right? Okay. No, what it's supposed to show in the very middle, this would be like at the mid-ocean ridge. Okay, so new ocean crust would be coming up to the surface and hardening there, right? And then everything else would be pushed away, yes? This would be like a top-down look. So notice, though, everything on this side is like an echo or whatever of this side. You guys see that? It's symmetrical, yes? It's like a pattern emanating from the middle. This little stripe here and this one, that rock was produced at the same time here. Follow? Yep. Okay. The stripes symbolize, I guess, represent magnetic orientation. So in other words, this strip of rock and this strip of rock came out at the same time from that rift in the ocean ridge and were oriented the same way. The magnetite minerals in the rock oriented to north. Does that make sense? The very next stripe, right there next to it, is oriented the other way. Because periodically, what does the Earth's magnetic field do? It flips. In other words, the north magnetic pole will become the southern magnet. Do you remember that? Okay. So what happens is we end up with a record on the sea floor of all of those flips. A record of it. Yeah. All right. So let's keep reading. What causes the strange stripes? I just told you. Seafloor magnetism, detected by magnetometers. You know how the destroyers looking for the submarines yesterday we talked about, right? They used the sonar, the echo sounders. Yep. They also used these magnetometers, which detect metal objects that have some, they're magnetic in their properties, or the actual magnetic orientation of the seafloor. Okay, makes sense, right? Because submarines are made out of steel, metal. Yeah. All right, polar reversals. We just talked about how they flip every however many thousands of years. It's not exactly the same each time. That's why, guys. That's why, for example, this stripe. These are the same, right? That's why these are wider than those. Because the magnetic field stayed with the same orientation longer, so more rock was put out during that time period, because it was a longer time period. Does that make sense? Okay. Moving on. Magnetic stripes. I like this graphic. Take a minute to look at this graphic. So we have, here's the mid-ocean ridge. Magma pushing up, okay? Underneath. What is going on underneath? Well, we'd have convection cells, convection currents going like this, right? Dragging the plates out, gap for new magma to come up, forming that mid-ocean ridge, right down the middle of which would be the rift, where new rock comes up and hardens. Does that make sense?
Yes, sir.
Okay. I'm going to do one more thing. put this in your notes. Draw along with me, if you will. Here is that. That's the crust.
That's the what?
That's the crust. That line is the crust of the earth. We're going to focus in on a mid-ocean ridge. Okay? In the mantle, you have material moving in convection cells. Okay? Why? Why does the mantle material move in convection cells? In convection currents? Because it's hot inside, deep within the earth, right? Can we agree? We watched the whole documentary, right? It's hotter the deeper you go. Okay? So if it's hot here and not as hot near the surface, can we agree on that? The material that is where it's hotter will become what? As it's heated, it becomes what?
Rock.
Less
Minerals.
dense.
Oh yeah, good job.
Okay? So as it's heated up, it becomes less dense, which means it does what? It rises. It floats to the top, guys. You guys remember how a lava lamp works? You got oil filled in the lava lamp. You got a wax ball in it. You turn the heat element on. The wax heats up, becomes less dense, rises to the top, gets further away from the heat element, cools down, gets more dense, and goes right back down. It's the same concept here. You have a heat source. The material becomes less dense, floats to the top, starts to cool off because it's not as hot up here. So it cools down, becomes what? More dense, and falls back down to be heated again. So we have a convection cycle, right? So this would be a convection cell. Each individually, we call that a convection cell. The whole thing, we would call all of them, we would call them convection currents, right? My handwriting is horrible. I know, I apologize. If I slowed way down, it would get better, but I'm not going to. All right, shh. So if we have this mantle material, which is like liquid-ish rock, right? It is going to have some interaction with the crust, agreed? The crust is resting on top of it. This is the asthenosphere up here. The lithosphere is on that. So you're going to have some friction. Even though it's going to flow past it, you're still going to have friction there. It's going to drag on it. So what's going to happen? This convection cell is going to drag the crust that way. But then this convection cell is going to drag the crust that way. It's like a tug of war on the crust. What's going to happen right there? It's going to break. You're going to tear it. There's going to be a tear. The word we use in here in this unit is a rift. Okay, there's going to be a rift in the middle. So we're going to have a gap form. We're going to pull it apart. What's going to happen? You're going to have some of that hot magma is going to rise up and fill the gap. It's going to fill the rift. Okay? So, and by the way, when that comes up, it's actually going to come up above the average seafloor depth, the average crust depth. So you end up with a what? A mid-ocean ridge. Okay? That's a mid-ocean ridge right there, just formed because that magma shot up through that gap. But it's still being pulled in opposite directions, so we still have our rift in the middle of the ridge. Does that make sense?
Yes, sir.
Awesome. Okay. Too much writing, too many different
Yeah,
colors?
it's almost like Aquaman.
This looks like
In the movie Aquaman.
Okay. All right.
They all do one package, right?
Now, we have the Earth's magnetic field will stay oriented the same way. North will be north for however many thousands of years. So maybe from here to here, all of that would be oriented the same way. The new rock would be oriented the same way. But then it's going to get dragged out, okay? And at some point, the Earth's magnetic field will flip, and the next one coming up, so that'd be move out, okay? This is older. And then we have new rock, and that would be pointed the other way. So you have these stripes. That's how the stripes form, okay? What else? This ocean crust, this oceanic crust, moving that way, eventually will run into something, yes? I don't know why I squared that off, whatever. So this would be what kind of crust? Continental. Continental crust. Continental crust is more dense or less dense than ocean crust? It's more dense. No, this is less dense. You tricked me. So, shh, a lot of talk and chatter. This is thinner and more dense, right, than the continental crust. So what is it going to do when they run into each other? Huh? So what's going to ride up on top? The ocean crust will subduct. Check it out. Shh. Good question. Okay? To subduct means to go beneath. Okay? So the ocean crust, being that it is thinner and more dense, is going to dive. It's going to dive beneath the continental crust. Now, as it does so, it's going to have some friction there too, isn't it? We have more friction right here. What's that friction going to do? Well, it's going to push on the continental crust. So we have the seafloor spreading because of the convection currents, pushes on friction interaction, right, with the continental crust. It's going to push on it. Continental drift. But also that friction, as this dives beneath the continental crust, is going to cause some partial melting of this crust. And it will release some things, right? So now we have, poking up through the edge of that continent, what do we have? Whoa, can't spell. Volcanoes.
There you go.
Okay? So on the edge of a lot of continents where there's a subduction zone just off the coast, there's going to be volcanoes, like a line of them. I'll give you an example. Go to my Google Earth, right along here. Check this out. Pacific Ocean is moving northwest. It's going to collide with the continental crust. As it does so, it subducts beneath. See this dark blue? Dark blue is the what? Deepest. It's the trenches. That's where the ocean crust is subducting under. And look what we have just inside there. Just like on our diagram here, the subduction zone just inside that, you have volcanoes. My mouse is misbehaving today. Just inside that subduction zone, we have a line of volcanic islands. The Japanese mainland, the little islands in between there in Russia, and the Aleutian chain, all of those are volcanic islands as a result of this subduction zone. Does that make sense?
Sure.
Sure? Let's keep reading. Seafloor ages. Okay, this one should be easy. Most of the classes today, it's been easy. Where is the seafloor the youngest? At the ridges or at the subduction zone?
Ridges.
It's the youngest here. This is where it's brand new. Okay? Check it out. When it's brand new, will there be much sediment on top of it? No, because it takes time for sediments to deposit upon it, right? So here, they'll be pretty plain. way over here, there's going to be a whole bunch of sediment because it's been millions of years of deposits. Does that make sense? So here, on the top side of that crust, it starts to grow. It gets thicker. Does that make sense?
Yes.
But check it out. On the bottom side, it's going to grow too. As this moves away from where it's the hottest, it starts to cool, right? As you go away from that rift, the magma starts to cool and it starts to actually solidify on the bottom side and make that crust thicker. Does that make sense? Kind of sort of maybe? Mouse is tweaking, yeah. All right, so the oldest seafloor is younger than 180 million years, according to the best research that we have right now. Okay? Side conversations. I can't believe y'all. The continental crust. Here it is. The oldest continental crust is about 4 billion years old with a B. Why is the continental crust able to get so much older than the ocean crust? Because ocean crust is constantly getting recycled, whereas the continental crust is just floating on top. Make sense?
Yep.
Awesome. All right, let's move to the next lesson. All right, guys, this guy, I'm serious. Has anybody watched old movies?
No.
Nobody's into old movies? Black and white old. Like what?
Oh, black and white.
Black and white.
Yeah, I know.
Okay. If you're interested in war movies too, like black and white war movies, Run Silent, Run Deep is a classic. It's a classic, guys. Yeah. This guy, Harry Hess, you should put it in your notes, geologist and U.S. Navy reservist officer. In this picture, he looks like Clark Gable. Like a young Clark Gable. He's got the mustache, the whole look with the Navy uniform. Clark Gable is an actor that was the main character in Run Silent, Run Deep. Co-star with Burt Lancaster. Harry Hess, H-E-S-S. Anyway, that's off topic that he looks like Clark Gable, but whatever. Big movie star in like the 40s. Clark Gable, huge. I know you weren't alive. I wasn't alive, and I'm ancient. All right.
You're not even what? I definitely was.
All right. Shh. So, Harry Hess, the geologist, remember on ship, right? From yesterday, the lesson. He starts to put all this evidence together, okay? And he has the last piece of the puzzle that Wegener didn't have. Hess understands, because there's other people that have figured it out. He didn't do it like in a vacuum. They figured out this. They figured out what's going on in the mantle. So he says that's the mechanism. That's the thing. The heat that's moving in the mantle is what pushes and pulls on the ocean crust. So it causes seafloor spreading, and seafloor spreading pushes on the continents. So you take continental drift, seafloor spreading, with the mechanism that drives it all, and you end up with plate tectonics. The concept, which will be our next couple of lessons. Okay? So it all kind of comes together. All right, questions on this?
No.
I did not read this, guys. You please, just to help lock it in, go ahead and read it. I'm not going to read it to you. All the lines of evidence come together. Blah, 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 blah. Mechanism, video, this is similar to the one that we watched, but you can watch it again. And there's your summary for this lesson. Seafloor spreading, mixture of different ideas and data, all put together. Harry Hess called his idea an essay in geopoetry. Okay. And seafloor spreading is the mechanism for the drifting continents, and convection currents in the mantle are the mechanism for the seafloor spreading, which we just mentioned. Okay. I'm going to head and assign these tomorrow. You probably finish them today, because I got through it pretty fast with you guys. Practice makes perfect, right?
Yeah.
Tomorrow will also be a work day. So take your time, do the reading, do it right. You'll have time. Tomorrow I'll also check your models of the Earth, the layers. I'm going to check it tomorrow. Doesn't have to be completely done, but it should be mostly done. And I'm going to give you a worksheet tomorrow that kind of covers the last few lessons.
I'm also making a theme.
Yes, they are, and they're reviewed. Guys, they're reviewed. It's just supposed to kind of reinforce. All right, here we go.